Hello there! And welcome to Smart Student TV, the only channel where academic and professional prowess is nurtured right from the comfort of your living room. Whether you are a student striving for excellence, a professional looking to sharpen your skills, or simply a lifelong learner, you are in the right place. In today's tutorial, we dive into another very exciting and important topic: vacuum technology. Have you ever wondered how scientists achieve incredibly precise results in experiments, or how industries create flawless electronic components and preserve delicate pharmaceuticals? Behind these marvels lies the invisible yet powerful force of vacuum technology. It's not just about removing air. It's about creating controlled environments where innovation thrives, precision reigns, and possibilities become limitless. For every aspiring lab technician, understanding vacuum technology isn't just an added skill. It's a gateway to becoming indispensable in any scientific or industrial setting. Imagine a world where delicate biological samples are preserved for decades, where electronic components are manufactured with zero defects, and where scientists can simulate the vast emptiness of space right here on Earth. This is the world of vacuum technology, a world where science meets precision and possibilities become realities. Whether you're an aspiring lab technician or a seasoned scientist, mastering vacuum technology will not only elevate your skills but also open doors to groundbreaking opportunities. So, buckle up as we embark on this fascinating journey into the world of vacuums. What is a vacuum? The word vacuum might sound intimidating, but it simply refers to a space that is void of matter or has extremely low pressure compared to the surrounding atmosphere. In simple terms, it is a space where air and other gases are significantly reduced, creating a condition often referred to as negative pressure. For example, think about a suction pump used to remove air from a sealed jar. The air inside gets sucked out, creating a partial vacuum. Objectives of this tutorial. By the end of this tutorial, you should be able to 1. Discuss the levels of vacuums. 2. Explain the types of vacuum. 3. Describe methods of vacuum production. 4. Discuss vacuum systems. 5. Identify types of vacuum pumps. 6. Understand types of vacuum gauges. 7. Discuss vacuum leakages. 8. Understand care and maintenance of vacuum systems. Applications of vacuum technology. 1. Medical industry. Vacuum pumps are used in surgical tools and sterilization processes. 2. Electronics manufacturing, creating microchips and thin films. 3. Food industry. Vacuum sealing to preserve food for longer periods. 4. Aerospace industry. Simulating space conditions for testing spacecraft equipment. 5. Chemical industry. Vacuum distillation and extraction. 6. Research laboratories. Particle accelerators and controlled experiments. Importance of vacuum technology in laboratory science. Vacuum technology plays a critical role in laboratory science. It is used in 1. Distillation processes, for separating chemicals at lower temperatures. 2. Drying samples, removing moisture without applying excessive heat. 3. Electron microscopy, providing a clear path for electron beams. 4. Freeze drying, preserving biological samples and pharmaceuticals. 5. Thin film coating, applying coatings on optical lenses and electronic devices. For a laboratory technician, understanding vacuum technology is essential because 1. It ensures accurate results in scientific experiments. 2. Prevents contamination during sample preparation. 3. Enhances efficiency in lab processes. 4. Enables proper maintenance and troubleshooting of vacuum systems. 5. Reduces operational costs by preventing unnecessary breakdowns. Introduction to vacuum technology. Vacuum technology isn't just for scientists in white lab coats. It plays a crucial role in industries like food preservation, electronics manufacturing, and even space exploration. So, grab a cup of coffee, sit back, and let's dive into the fascinating world of vacuums. Levels of vacuum. When we talk about a vacuum, we're essentially talking about a space where there's very little or almost no matter, especially air or gas. But let's be honest, Achieving a space that's completely empty, with zero particles, is pretty much impossible with our current technology. So instead, scientists and engineers break vacuums down into different levels based on how much pressure is left in the space. These levels are measured in millibars, mbar, or pascals pa. 1. Rough vacuum. The first level is called a rough vacuum, also known as low vacuum, 760 to 25 torr. Think of this as the entry-level vacuum, where the pressure is reduced but not to any extreme degree. Rough vacuums are commonly used in industries for tasks like vacuum sealing food packages to keep them fresh for longer. When you buy a bag of vacuum-sealed coffee, that's a rough vacuum at work. 2. Fine vacuum. Next up, we have the fine vacuum, also referred to as medium vacuum. Here, the pressure drops even further, and this type of vacuum is often used in more specialized applications, like freeze-drying food or applying thin coatings to materials. For example, when manufacturers coat electronic components with protective layers, they often rely on a fine vacuum to get the job done. 3. High vacuum. Moving even lower, we enter the high vacuum range. At this level, air molecules become extremely sparse. High vacuums are essential in advanced scientific research, such as particle accelerators or mass spectrometers, where even a tiny molecule of air can mess up an experiment. 4. Very high vacuum. If we go even deeper, we reach the very high vacuum. This level is so rarefied that it requires extremely advanced technology to maintain. You'd typically find very high vacuums in high-precision experiments, like studying nanotechnology surfaces or space simulations. 5. Ultra-high vacuum. Finally, there's the ultra-high vacuum. This level of vacuum represents the lowest pressure achievable with current technology. Ultra-high vacuums are used in the most sensitive experiments, where even a single gas molecule could disrupt results. Types of vacuum. Now that we've talked about levels, let's look at the different types of vacuum. First, there's the partial vacuum. This is what happens when some air or gas is removed, but not all of it. A great example of this is your regular household vacuum cleaner. It doesn't remove all the air, it just reduces the pressure enough to suck up dust and dirt. Then we have the hard vacuum. This is a much lower pressure environment, where there are very few gas particles left. Think of research facilities that simulate outer space. They rely on hard vacuums to replicate those conditions. Lastly, there's the perfect vacuum. Now, this one's purely theoretical. A perfect vacuum would mean zero particles, and unfortunately, we haven't figured out how to make that happen yet. But scientists still use it as a reference point in their calculations and theoretical studies. Methods of vacuum production. Alright, so how do we actually create a vacuum? Well, there are several methods, each suited to different levels and types of vacuum. One common method involves mechanical pumps, like rotary vane pumps or diaphragm pumps. These pumps work by physically removing air and gas from a chamber. They're great for achieving rough and fine vacuums and are widely used in both industrial and scientific settings. For higher vacuums, we often rely on diffusion pumps. These pumps use high-speed jets of vapor to trap and remove gas molecules. They're particularly effective for achieving high vacuum levels in systems like electron microscopes. Then we have cryogenic pumps. These pumps use extremely low temperatures to condense and freeze gas molecules, effectively trapping them. They're essential for creating ultra-high vacuums. Lastly, there are turbomolecular pumps. These are high-speed pumps with rotating blades that literally push gas molecules out of the chamber. They're often used in both high and ultra-high vacuum systems. Vacuum systems. A complete vacuum system isn't just about the pump. It's a whole setup with several key components working together. At the heart of it all is the vacuum pump, which does the heavy lifting by removing air and gas from the chamber. Then there's the vacuum chamber itself, which is the sealed space where the vacuum is created. You can think of it as the workspace where all the magic happens. To control the flow of gas in and out of the system, we use valves and pipes. These components help maintain the right pressure and prevent unwanted leaks. Of course, we also need a way to measure how much vacuum we've achieved. That's where measuring gauges come in. They provide real-time data on the pressure inside the system. Lastly, there are sealing mechanisms. These ensure that no air sneaks into the system from the outside. Think of them as the guardians of the vacuum chamber. Understanding how these components work together is crucial for designing and operating vacuum systems effectively. Whether you're sealing food packages, experimenting with nanotechnology, or simulating the vacuum of outer space. Vacuum pumps. At its core, vacuum technology is all about creating and measuring a space devoid of air, or, more technically, a space where the pressure is significantly lower than atmospheric pressure. To achieve this, scientists and engineers use specialized tools known as vacuum pumps and vacuum gauges. Today, we'll take a deep dive into the fascinating world of these tools, breaking them down into simple explanations that anyone can understand. Let's start with vacuum pumps. Imagine you're trying to suck air out of a balloon with your mouth. At first, it's easy because there's a lot of air inside. But as the balloon gets emptier, it becomes harder to pull out the remaining air. Vacuum pumps work on a similar principle. They're designed to remove air or other gases from a sealed space, creating a vacuum. Depending on the type of vacuum needed, whether rough, high, or ultra-high vacuum, different types of pumps are used. First up, we have rotary vane pumps. These are the workhorses of the vacuum world and are commonly used for rough vacuum applications. Picture a spinning wheel with small vanes attached, working inside a sealed chamber. As the wheel spins, the vanes trap pockets of air and push them out of the pump. It's like a revolving door for air molecules. Rotary vane pumps are popular because they're reliable, relatively affordable, and easy to maintain. They're used in laboratories, air conditioning systems, and even in food packaging where vacuum-sealed products stay fresh longer. Next, we have Roots pumps. These pumps are designed for high-capacity pumping, meaning they can move large volumes of gas quickly. Imagine two figure-8-shaped rotors spinning in opposite directions inside a sealed chamber. As they spin, they trap and move air from one side of the pump to the other without compressing it. Roots pumps are incredibly efficient when you need to evacuate large spaces rapidly, such as in industrial vacuum systems or chemical processing plants. However, they usually work in combination with other pumps because they can't achieve a very high vacuum on their own. Now let's talk about diffusion pumps. These pumps are used when we need high or even ultra-high vacuum conditions, like in semiconductor manufacturing or space simulation chambers. Instead of mechanical movement, diffusion pumps rely on high-speed jets of vapor, usually oil, to carry gas molecules out of the vacuum chamber. Think of it like a waterfall pulling small leaves down with its flow. Diffusion pumps are powerful and can achieve extremely low pressures, but they require careful maintenance and monitoring because the oil used in them can degrade over time. Cryo pumps, on the other hand, are like freezers for gases. They work by cooling certain surfaces to extremely low temperatures, causing gas molecules to freeze and stick to those surfaces. Imagine a cold soda can on a hot day with water droplets forming on the surface. Cryo pumps essentially freeze gas molecules out of the vacuum chamber, creating an ultra-clean and particle-free vacuum. They're often used in applications where cleanliness is paramount, such as in semiconductor production or advanced research labs. Finally, we have turbomolecular pumps. These pumps are precision tools designed for creating and maintaining ultra-high vacuums. They use a series of high-speed rotating blades to literally chop and push gas molecules out of the vacuum chamber. Picture a fan spinning at an incredibly high speed, directing air in a specific direction. Turbomolecular pumps are incredibly precise and are often paired with other pumps, like rotary vane pumps, to achieve the desired vacuum level. They're commonly found in mass spectrometers, electron microscopes, and particle accelerators. Vacuum gauges. Now that we've explored vacuum pumps, let's switch gears and talk about vacuum gauges. After all, what's the point of creating a vacuum if you can't measure it accurately? Vacuum gauges are tools designed to measure the level of vacuum in a system, and just like pumps, different types are used for different pressure ranges. Manometers are the simplest type of vacuum gauge and are typically used to measure rough vacuums. They work based on the principle of fluid displacement. Imagine a U-shaped tube partially filled with liquid, usually mercury or oil. When air pressure changes on one side of the tube, the liquid level shifts, and the difference in height gives you a measurement of the pressure. Manometers are straightforward, reliable, and great for low vacuum applications, such as HVAC systems or basic lab setups. Pirani gauges, on the other hand, are thermal conductivity gauges. They measure vacuum levels by looking at how well a gas conducts heat. Inside the gauge, there's a tiny heated wire. In a high-pressure environment, gas molecules bump into the wire frequently, carrying heat away and keeping the wire cool. But as the vacuum level increases and fewer gas molecules remain, the wire retains more heat. By measuring the temperature change, a Pirani gauge can give you an accurate vacuum reading. These gauges are widely used in industrial vacuum systems and scientific research. 2. Ionization gauges. Ionization gauges are used for ultra-high vacuum measurements. These gauges work by ionizing gas molecules in the vacuum chamber using an electron beam. Once ionized, the gas molecules are attracted to a charged collector plate, and the resulting current is measured. The lower the number of gas molecules in the vacuum, the lower the current. Ionization gauges are incredibly sensitive and can measure extremely low pressures, making them essential for applications in space simulation, advanced physics experiments, and ultra-clean manufacturing environments. 3. McLeod gauges. McLeod gauges are another type of vacuum gauge used for precise low-pressure measurements. They operate by compressing a known volume of gas and measuring the resulting pressure. These gauges are highly accurate but are somewhat bulky and less commonly used in modern systems. 4. Vacustat gauges. Vacustat gauges are compact and often used for monitoring vacuum levels in industrial processes. They provide simple on-off control signals based on preset pressure levels, making them ideal for automated systems. 4. Thermocouple gauges. Thermocouple gauges measure pressure by monitoring the temperature of a heated wire in a vacuum environment. Similar to Pirani gauges, they rely on thermal conductivity but use thermocouples to measure the temperature changes. 5. Penning gauges. Penning gauges, also known as cold cathode ionization gauges, are used for ultra-high vacuum measurements. They ionize gas molecules using an electric discharge, and the resulting ion current is measured to determine pressure. In summary, vacuum technology relies heavily on both pumps and gauges to create and monitor vacuum conditions. Whether it's a rough vacuum needed for food packaging or an ultra-high vacuum required for cutting-edge scientific research, the right combination of pumps and gauges ensures precision, reliability, and efficiency. Understanding these tools not only gives us insight into their fascinating mechanisms, but also highlights their importance in shaping the modern world. So, the next time you see a vacuum-sealed bag of coffee or hear about groundbreaking space experiments, you'll know the quiet heroes behind them are vacuum pumps and gauges, working tirelessly to create invisible but essential spaces. Vacuum leakages. Imagine you're trying to keep air out of a sealed glass jar. You tighten the lid as much as you can, but if there's even a tiny crack or an improperly fitted seal, air will sneak in. That's essentially what happens in a vacuum system when there's a leakage. Vacuum systems are designed to create and maintain low-pressure environments, but when a leak occurs, air or other gases infiltrate the system, disrupting its efficiency. Why are leakages a problem? Leakages in vacuum systems can lead to multiple issues. For instance, in a pharmaceutical lab, a leak might compromise the sterility of a product. In an electronics manufacturing setting, it could cause defects in sensitive components. In space applications, vacuum integrity is literally a matter of life and death. So, detecting and sealing leaks isn't just about efficiency. It's often about safety and product quality. Types of vacuum leakages. Vacuum leakages are generally classified into two main categories: real leaks and virtual leaks. 1. Real leaks. A real leak is exactly what it sounds like: a physical hole, crack, or gap in the system that allows gas to flow in or out. These leaks are usually caused by manufacturing defects, material fatigue, or damage during operation. For example, if a glass vacuum chamber develops a hairline crack, air will seep in through that crack. 2. Virtual leaks. Now, virtual leaks are a bit trickier. These aren't actual holes, but rather pockets of trapped gas within the system itself. Over time, these trapped gases are slowly released into the vacuum environment, creating what seems like a leak. Think of it like a sponge soaked in water. Even if the sponge isn't actively leaking, small droplets of water can still escape over time. Causes of vacuum leakages. Understanding the causes of vacuum leakages is crucial for preventing them. Some of the most common culprits include 1. Faulty O-rings. O-rings are rubber or silicone seals used in vacuum systems to ensure airtight connections. However, over time, they can degrade, crack, or lose their elasticity, leading to leaks. 2. Loose fittings. Sometimes, leaks are as simple as a loose bolt or an improperly tightened flange. Even a tiny misalignment can create a pathway for air to sneak in. 3. Cracked glassware. Glass is often used in vacuum systems because of its non-reactive nature and transparency. But glass is also brittle and prone to cracking under stress or temperature fluctuations. 4. Material defects. Manufacturing flaws, such as tiny pores in metal surfaces or improperly machined parts, can also be sources of leaks. Methods for detecting vacuum leakages. Detecting a vacuum leak is both an art and a science. There are several techniques available, each with its own advantages and limitations. 1. Bubble test. The bubble test is one of the simplest and most visual methods for detecting leaks. A soap solution is applied to suspected leak points, and if there's a leak, bubbles will form as the gas escapes. While this method is low-tech, it's surprisingly effective for identifying larger leaks. 2. Pressure rise test. In this method, the vacuum system is sealed and isolated, and then the pressure inside is monitored over time. If the pressure rises steadily, it indicates that gas is leaking into the system. 3. Helium leak test. For more precise leak detection, the helium leak test is often used. Helium is introduced into the system as a tracer gas, and a sensitive detector is used to identify its presence at potential leak points. Helium is ideal for this test because it is non-reactive, lightweight, and easy to detect. Sealing vacuum leakages. Once a leak is detected, the next step is to seal it effectively. This often involves a combination of techniques and materials. 1. Proper tightening of joints. Loose joints and fittings are a common cause of leaks, so ensuring that all connections are properly tightened is the first step. 2. Using high-quality O-rings. Replacing old worn-out O-rings with high-quality, vacuum-compatible alternatives can often resolve leakage issues. 3. Applying vacuum-compatible sealants. Specialized sealants designed for vacuum environments can be applied to small cracks or imperfections to create airtight seals. Vacuum leakages might seem like a highly technical problem, but at their core, they're about maintaining control over an environment. Whether it's ensuring the sterility of a pharmaceutical product, the precision of an electronic component, or the safety of astronauts in space, addressing vacuum leaks is a fundamental part of managing vacuum systems effectively. So, whether you're a student learning about vacuum technology for the first time or an experienced engineer troubleshooting a problematic system, understanding the causes, types, detection methods, and sealing techniques of vacuum leakages will equip you with the tools you need to tackle this persistent challenge head-on. With patience, precision, and a good grasp of these principles, vacuum leaks can be identified, managed, and resolved effectively. Finally, let's finish by discussing care and maintenance of vacuum systems. Vacuum systems are crucial tools in various scientific, industrial, and laboratory applications. Whether you're working in research, manufacturing, or environmental testing, maintaining a vacuum system is essential for ensuring that it performs effectively and reliably. A well-maintained vacuum system not only helps improve the quality of results, but also extends the lifespan of the equipment. In this tutorial, we'll cover the best practices for caring for and maintaining vacuum systems, including the inspection of pumps and seals, cleaning chambers and pipelines, lubricating moving parts, and replacing worn-out components. 1. Regular inspection of pumps and seals. The heart of any vacuum system is the pump, which creates the necessary vacuum by removing air or gases from the system. Regularly inspecting the pump is key to keeping the vacuum system in optimal condition. Why inspection matters. Early detection of faults. Regular checks help identify issues before they turn into major problems. Maintaining performance. If a pump becomes worn out or inefficient, it will struggle to maintain the required vacuum levels, leading to poor results and potential system failure. Energy efficiency. A well-maintained pump runs more efficiently, saving energy and reducing operating costs. How to inspect the pump. Visual checks. Look for any signs of wear and tear, such as cracks, leaks, or oil stains around the pump. These are indicators that the pump may not be functioning correctly. Check for unusual noises. A vacuum pump should operate smoothly and quietly. If you hear strange sounds like grinding or squeaking, it might indicate a mechanical issue. Check the motor and power supply. Ensure that the motor is working correctly and the power supply is stable. Inconsistent power can cause the pump to operate inefficiently. Vacuum pressure. Use a pressure gauge to monitor the vacuum pressure. If the pressure is not dropping as expected, the pump might be losing efficiency or there could be leaks in the system. Inspecting seals. Seals are responsible for maintaining the vacuum by preventing leaks. Over time, seals can degrade due to constant exposure to pressure, heat, and chemical exposure. Signs of seal wear. Check for cracks, brittleness, or leaks around the seals. If a seal is damaged, it will compromise the vacuum and lead to inefficiencies. Test for leaks. A simple test involves spraying a leak-detecting solution or using a helium leak detector to identify areas where air may be entering the system. 2. Cleaning chambers and pipelines. Keeping the vacuum chamber and pipelines clean is vital for maintaining system performance and ensuring the quality of any processes that rely on the vacuum system, such as chemical reactions or material handling. Why cleaning is important. Prevent contamination. Dust, debris, and chemical residues can contaminate the system and affect the results of your experiments or processes. Prevent blockages. Dirt and debris can accumulate in pipelines and valves, potentially causing blockages that interfere with the vacuum process. Maintaining efficiency. A clean system ensures that air or gas flows smoothly through the chamber and pipelines, allowing the vacuum system to operate at its best. How to clean the vacuum system. Chamber cleaning. Depending on the nature of the work you're doing, chambers can accumulate dust, dirt, or chemical residues. Use a soft, lint-free cloth to wipe the inside surfaces of the chamber. If there are stubborn residues, consider using a non-abrasive cleaning agent that is safe for the materials in the chamber. Pipeline cleaning. Regularly check the pipelines for dirt and chemical deposits. For hard-to-reach areas, use a soft brush or cleaning swab. Avoid using harsh chemicals that might damage the pipelines. In some cases, it may be necessary to flush the system with a cleaning solvent or use a vacuum cleaner specifically designed for such purposes. Filters. If your vacuum system has filters, clean or replace them regularly. Filters trap particles and contaminants, but over time, they can become clogged and reduce the efficiency of the system. 3. Lubricating moving parts. Moving parts such as motors, pistons, and valves require lubrication to function smoothly. Proper lubrication reduces friction, prevents wear, and ensures that the system operates quietly and efficiently. Why lubrication is necessary. Prevents damage. Without adequate lubrication, moving parts can wear out quickly due to friction, leading to costly repairs or replacements. Improves efficiency. Lubrication ensures that the components move smoothly, reducing energy consumption and wear on the parts. Reduces noise. Properly lubricated parts run more quietly, which can be important in laboratory settings where noise can be disruptive. 4. Immediate replacement of worn-out parts. No matter how well you maintain your vacuum system, parts will wear out over time. This is particularly true for components that experience heavy use, such as seals, valves, and pumps. How to identify worn-out parts. Check for visible damage. Look for cracks, tears, or other signs of wear, especially in seals and gaskets. Performance decline. If the system is having trouble reaching or maintaining the desired vacuum level, this might indicate that parts are no longer functioning properly. Monitor for leaks. Leaks are often a sign that seals or other components need replacement. Replacing worn-out parts. Consult the manufacturer. Always refer to the user manual to ensure you're using the correct parts for replacement. Timely replacement. Replace parts as soon as they show signs of wear, and never wait until the part fails completely. Safety precautions when handling vacuum systems. Vacuum systems, while incredibly useful, can pose significant safety risks if not handled properly. Here are some important safety precautions to follow when working with these systems. 1. Always wear protective equipment. Safety should always be a priority when operating any vacuum system. Wear appropriate protective gear to minimize the risk of injury. 2. Avoid sudden pressure changes. Vacuum systems work by creating a pressure difference, and sudden changes in pressure can cause catastrophic damage to the system or even harm personnel. 3. Regularly monitor pressure gauges. Pressure gauges are essential for ensuring that your vacuum system is operating within the safe pressure range. Monitoring the pressure regularly helps you avoid exceeding the system's design limits. 4. Ensure proper ventilation in the lab. Vacuum systems can create hazards by trapping gases, fumes, or vapors. Ensure that the lab is well ventilated to avoid a dangerous buildup of hazardous substances. 5. Train personnel on emergency procedures. Accidents can happen, and it's important to be prepared. Training staff and personnel on how to handle emergencies can prevent injuries and damage to equipment. Regular inspection of pumps and seals, cleaning of chambers and pipelines, lubricating moving parts, and timely replacement of worn-out components are all crucial for maintaining the system's functionality. Equally important are the safety precautions, including wearing protective gear, avoiding sudden pressure changes, monitoring pressure gauges, ensuring proper ventilation, and training personnel in emergency procedures. By following these care and safety tips, you can ensure that your vacuum system remains reliable and safe for use in your work environment.